Hi everyone, I'm Adrian from the Australian Computing Museum, or the ACMS, based here in Sydney, New South Wales, Australia. At the ACMS, we have one of the largest digital equipment corporation collections anywhere in the world. We were founded in 1994 by many people, including Max Burnett, one of the first employees of Digital Australia. DEC was founded in 1957 in Maynard, Massachusetts, and grew to be one of the largest computing companies in the world. In our collection, we have a significant amount of documents, computers, and training material. And today, we're going to present some of that training material to you in the form of old VHS tapes. So please sit back, relax, and enjoy. Thank you.
The architecture of a computer defines the instructions executed by the CPU, the format of instructions, the way the computer stores and accesses data, and so on. This unit describes the elements that make up the VAX architecture. The best way to describe this architecture is to present it from the viewpoint of the assembly language programmer. Our goal is not to teach assembly language programming, but to give you a broad overview of the architecture which is common to all VAX computers. The unit introduction in your course reference guide briefly discusses assembly language programming and how it relates to elementary computer operations. If you're not familiar with programming at the assembly language level, please stop the videotape and read the introduction before going on. In this unit, we'll concentrate on three main elements of the VAX architecture: the data types, instruction set, and addressing mode. Lesson 1 describes the data types that are operated upon by VAX instructions. The data type determines how a pattern of bits is interpreted by the CPU. Lesson 2 introduces the instruction set that's executed by the CPU. There are over 300 instructions. We won't cover them all, but we'll describe many of the more commonly used instructions. Lesson 3 describes the addressing modes that tell the CPU how to access the data to be operated upon. These addressing modes are used in combination with the general registers discussed in the previous unit. The unit closes with an example of a program segment showing how these three elements of the architecture work together.
When computers perform operations, they work with binary units called bits. Bits by themselves have little meaning unless they're grouped together into larger units that can be treated as separate entities. The basic information unit is the 8-bit byte. As we'll see shortly, VAX computers work with larger units as well. On a VAX, bit positions within a byte are numbered from right to left, starting with 0. Bit 0 is always the least significant bit, or low-order bit. Bit positions increase in significance toward the left, ending with bit 7, the most significant bit, or high-order bit. While bytes are useful for certain kinds of data types and operations, larger information units consisting of 2 or more bytes are also necessary. A word contains 2 bytes, or 16 bits. Bit 15 is the most significant bit. 2 words, or 4 bytes, make up a larger information unit called a long word. 2 long words comprise a quad word, which contains 8 bytes, or 64 bits. The octaword is the largest unit defined in the VAX architecture. It consists of 16 bytes and is used only with certain data types and operations. Each of these information units is located in memory by the address of its first byte. These 5 units form the basis of a variety of data types. A data type indicates how the binary contents of an information unit are to be interpreted when the CPU executes an instruction. For example, these 2 words contain the same binary values. However, the data they represent can be entirely different, depending upon the data type in use. There are 3 general categories of data types defined in the VAX architecture: arithmetic data types, string data types, and a unique data type called the variable length bit field. We'll examine each of these data types briefly. Information is also included in your course reference guide. Let's begin with the arithmetic data types. There are two kinds of arithmetic data types, integers and floating point data. Integers are whole numbers with positive or negative values. Integers can be signed or unsigned. That is, they can contain an explicit plus or minus sign, or neither. A signed integer uses the most significant bit to indicate the sign. If the signed bit is 0, the integer is positive. Conversely, if the signed bit contains a 1, the integer has a negative value. 5 integer data types are available based on the size of the information unit used to represent the data. Integers can be stored as bytes, words, long words, quad words, or even octawords. For certain applications, it's necessary to use the floating point data types in place of integers. Floating point notation is used to represent very large or very small numbers, such as those encountered in scientific or engineering applications. Here are two examples of floating point numbers, compared with the same values expressed in integer or decimal form. The floating point numbers are more compact and much easier to work with. A floating point number consists of 3 elements. The sign simply indicates a positive or negative value. Next is the fractional part of the number. This fractional part is multiplied by an exponent part. Note that the exponent is expressed as a power of 2 rather than 10. In a VAX computer, this number is represented using one of the floating point data types. In this case, we're using the F floating datum. The other floating data types have a similar format. Bit 15 is always designated as the sign bit. The fractional part of the number is represented by this field of the floating datum. The number of bits in this field determines the degree of precision. More bits allow greater precision. The F floating datum permits a precision of about 7 decimal digits. The binary exponent is designated in this part of the floating datum. The number of bits allocated for the exponent field determines the range of values that can be represented. 4 floating point data types are defined in the VAX architecture. This table shows the range of exponents and degree of precision that can be represented by each type. The F floating and D floating types permit the same range of exponent values. Notice, however, that the D floating datum allows more than double the precision of the F floating datum. Up to 16 digits can be expressed using the D floating data type. The G floating and H floating data types can accommodate a greater range of exponent values. In addition, the H floating datum provides 33 decimal digits of precision, more than twice that of the G floating datum. An expanded version of this table is included in your course reference guide. To recap, the VAX architecture allows programmers to perform arithmetic operations on 2 kinds of data, integers and floating point numbers. VAX also allows us to work with other kinds of data. One of these is the string. Strings are useful for representing character sequences and numbers that will not be used for computation. Because VAX treats characters and numbers somewhat differently, strings are classified into character strings and numeric strings. Character strings can represent any keyboard character: numbers, letters, blank spaces, and special symbols. Each character requires 1 byte of storage. The length of a character string is not fixed. A single string can contain over 65,000 bytes. Numbers may be treated as character strings, just like any other keyboard characters. Or, numbers with an explicit plus or minus sign may be represented as numeric strings. Absolute precision of up to 32 digits is possible using a numeric string. There are 3 kinds of numeric strings: leading separate strings, trailing strings, and packed decimal. In a leading separate string, the sign always precedes the number. The string uses 1 byte for the sign and a separate byte for each number. Leading separate strings are used when you want the output to appear with the sign preceding the number. The trailing numeric string also handles signed numbers. However, the sign is not separate, but is embedded with the last number. The last byte stores both a sign and a number. Because the sign doesn't need a byte of its own, this data type requires 1 less byte of storage. A typical use for the trailing numeric string is in commercial applications where a number is entered first and the sign is indicated afterwards, such as accounting debits and credits. A third numeric string, packed decimal, packs numeric values and the sign into even fewer bytes. Each byte holds 2 digits rather than a single digit. Notice that the last byte in the string contains a digit and the sign. Of the 3 numeric strings, packed decimal is the only string that can be used for arithmetic operations. Because each string has different attributes and uses, it may be necessary to convert from one numeric string to another. For example, you might use leading separate strings to input numbers for calculating an interest payment on some balance. You could then convert the leading separate strings to the packed decimal format so that the necessary calculations can be performed. Once the interest payment is calculated, you can convert back to a leading separate string so that the result would print out with the sign where you want it. All of these data types use a byte or a combination of bytes. There are times when it may be necessary or convenient to work with data in units smaller than 1 byte. The variable length bit field allows us to work with as little as 1 bit at a time. This data type differs from the others in 2 respects. First, its length is not fixed, but can vary from as few as 0 to as many as 32 contiguous bits. Second, the bit field does not have to begin on a byte boundary. It can begin anywhere in memory. A variable length bit field is defined by 3 attributes: its base address, a position, and a size. The base address establishes a reference point from which the location of the bit field is determined. The position then defines the actual location of the bit field relative to the base address. In other words, the position represents a displacement or offset from the base address. Here, the bit field is positioned 5 bits from the base address. The size of the bit field is defined by the 3rd attribute. This attribute indicates how many bits are to be operated on. The size can range from 0 to 32 bits. The variable length bit field allows programmers to pack fields of information tightly together to conserve storage. We'll use these 3 bit fields to illustrate the advantage of using the variable length bit field. Without the variable length bit field, these 3 fields require 5 bytes of storage. Some storage space is wasted because each field must begin on a byte boundary. With the variable length bit field, these same fields need only 3 bytes of storage. 2 bytes are saved because it's not necessary for each field to begin on a byte boundary. As we've seen in this lesson, the VAX architecture defines a wide variety of data types for different applications and operations. Some of these data types are used frequently, others rarely. In the next lesson, we'll describe some of the instructions that enable programmers to operate on these data types or to convert from one data type to another. This concludes the lesson on VAX data types. Please turn to your course reference guide for further study. In Lesson 1, we examined the types of data that can be operated on. In this lesson, we'll describe some of the instructions that direct the operation of the CPU. In general, an instruction specifies a single operation or function to be performed by the CPU, such as an add operation. Some instructions perform several operations in sequence. One instruction, for example, adds 2 operands, compares the sum to another value, and then branches based on the comparison. Let's look at the general format of a VAX instruction. VAX instructions typically contain 2 parts: an operator and 1 or more operand specifiers. If no data is referenced, no operand specifiers are needed. The operator defines the operation to be performed and the data type to be manipulated when the instruction is executed by the CPU. The operand specifiers define the locations of the data to be operated upon by the CPU. Here, for example, is the instruction to add 2 integer long words located in general registers R1 and R2. This instruction consists of 2 parts: an operator and 2 operand specifiers. Add designates an addition operation to be performed on a given number of operands. The letter L specifies the data type, integer long word. 2 designates the number of operands referenced by this particular instruction. Arithmetic operations can be performed on 2 or 3 operands. The operator portion of this instruction then specifies that an add operation is to be performed on 2 integer long-word operands. On the operand specifier side, R1 and R2 represent the location of the operands. The first operand is called the source operand. The second is the destination operand. R1 and R2 designate 2 of the 16 general registers within the CPU. Let's see how this add instruction works. Initially, the program counter, or PC, contains the address of this add instruction, so that the CPU can fetch it from memory. When the instruction is fetched, the PC is automatically updated to point to the next instruction. Meanwhile, the add instruction is executed in the CPU. The operands contained in registers R1 and R2 are added together by the arithmetic logic unit, or ALU. The result of the calculation is then placed in the location of the second operand. So in this case, the sum of R1 and R2 is returned to R2. The result of the add operation is also reflected in the condition codes of the processor status longword, or PSL, register. Recall that these 4 condition code bits are set when an operation produces a negative, 0, overflow, or carry result. If any of these conditions occurs during this add instruction, the corresponding bit is set. This lesson focuses on the operator part of the instruction. The operand specifiers will be the focus of Lesson 3. We'll divide the VAX instruction set into 3 general categories based on the type of operation or function performed. The first category consists of instructions that manipulate data. Included in this category are instructions that perform arithmetic, logical, transfer, and conversion operations. There are also instructions that operate on particular data types and structures, such as character strings, bit fields, stacks, and queues. The second category of instructions has to do with program control. These instructions generally do not operate on data. Rather, they alter the flow of program execution by changing the value of the program counter. Program control operations include jump, branch, case, loop, call, and return. The third category of instructions are called special purpose. Included in this category are instructions that can be executed only when the CPU is operating in a privileged access mode. Examples of the kinds of operations included in this category are halt and change mode. There are a number of other types as well. The VAX instruction set contains over 300 instructions to perform a wide assortment of operations. Your course reference guide contains a list of VAX instructions organized by these general categories. In this lesson, we'll sample several representative instructions from each category. Let's begin with data manipulation. There are instructions that perform the 4 basic arithmetic operations: add, subtract, multiply, and divide. Arithmetic operations can be performed on 3 kinds of data: integers, floating point numbers, and packed decimal strings. Of all the string data types, packed decimal is the only format that can be used for arithmetic operations. Most arithmetic instructions are provided in 2 formats: 2 operand instructions and 3 operand instructions. In a 2 operand instruction, the contents of 2 storage locations are operated on, and the result is stored in the second location. In this example, A is added to B, and the sum is stored in B. A 3 operand instruction uses a third location to store the results of an operation. Here, A is added to B. The sum is then stored in location C. In addition to the 4 basic arithmetic operations, a number of other operations are possible. For example, integers can be incremented or decremented by a value of 1. Also, long-word and quad-word integers can be shifted left or right. Shifting to the left is equivalent to multiplying the integer by a power of 2. Shifting to the right is equivalent to dividing by a power of 2. There's also a group of logical instructions that can be used to operate selected bits within a register or memory location. These bits do not have to be contiguous. Logical instructions are provided to set or clear bits, to test bits, or to complement them. These operations may be performed on one bit or on any number of selected bits, such as the 5 bits identified in this example. Transfer instructions represent another group of data manipulation instructions. Move instructions transfer data from one location to another. There are instructions for moving bytes, words, long words, quad words, and octawords. Another instruction moves the address of the data rather than the actual data. This instruction allows a programmer to place the address of a list or table into a base register. In addition, there are clear instructions for placing a 0 value into a register or memory location. These and other transfer instructions are listed in your course reference guide. The VAX architecture also provides several instructions for converting from one data type to another. Many different conversions are possible, such as the one shown here. For example, you can convert a leading numeric string to a packed decimal string, perform an arithmetic operation on the packed decimal value, and then convert the result back to a leading separate string. Thus, conversion instructions simplify the task of converting from one data type to another. Another set of instructions are used for queue manipulation. Insert adds an entry to a queue. Remove, in turn, takes an item out of a queue. Queue instructions automatically update the queue pointers. Items can be added to or removed from any position within the queue. Many other data manipulation instructions are defined in the VAX architecture, such as those for manipulating character strings, bit fields, and stacks. For more information, consult your course reference guide or one of the reference books listed in the guide. The second category of instructions, program control, are used to change the flow of program execution. These instructions alter the contents of the program counter to change the instruction sequence. Let's look at a few examples. There are unconditional branch instructions which always transfer program control to the branch destination. These instructions don't test values, bits, or condition codes. Many variations of conditional branch instructions are defined, which transfer control only if some condition is met or some value is matched. In this example, the branch will occur if the 0 condition code bit, or Z bit, contains a 1. The branch will not occur if the Z bit is 0. The case instruction is an example of a program control instruction that performs a more sophisticated operation, multiple conditional branches. The value of a variable index determines which branch will be taken when the program executes. Loop instructions are also provided. In this example, the variable A is used to count the number of program loops. A is incremented by 1 each time another loop is completed. When A reaches 75, the program exits from this loop. These operations are performed by a single loop instruction. Another program control instruction, the procedure call, is used to transfer control to a procedure from any point in the main program. One of the features of this call instruction is that it automatically passes an argument list from the main program to the procedure. The argument list contains data or addresses to be used by the procedure. Once the procedure starts executing, it locates the list of arguments using the address in register 12, the argument pointer. At the end of the procedure, a return from procedure instruction returns control back to the main program. The VAX architecture defines a calling standard so that procedures written in any language can be called in the same way. Our third category of instructions includes special purpose instructions, which are used mainly to write system code. For most of these instructions, access is permitted to VMS only. Privileged instructions, such as halting the system, cannot be made available to users. One group of instructions is related to the access mode in which the CPU is executing. These change mode instructions allow VMS to change the processor access mode when necessary. 4 different access modes are possible, each with a different level of privilege. The processor status long word contains a group of bits that store information about the processor access mode. Change mode instructions change the contents of these bits to reflect the new access mode. This completes Lesson 2. In this lesson, we've looked at some of the instructions that are implemented as part of the VAX architecture. In the next lesson, we'll examine another aspect of the VAX architecture, the addressing modes which are used to access operands referenced by these instructions. Additional information related to the VAX instruction set is provided in your course reference guide. Please turn now to the guide to review the material covered on the videotape. In the previous lesson, we looked at the VAX instruction set. In this lesson, we'll examine the addressing modes that provide the information needed to locate the data referenced by instructions. As explained in Lesson 2, a typical VAX instruction consists of an operator part and one or more operand specifiers. The operator defines the operation to be performed and, where applicable, the data type to be manipulated. The operand specifiers also contain two kinds of information. They determine which general registers are to be used to carry out the instruction. In addition, they specify the addressing modes that determine how these registers are to be used. As we'll see, the VAX architecture provides a variety of addressing modes. Each has a name that describes how that mode is used. We won't cover all of the addressing modes in this lesson. Rather, we'll examine the representative modes listed here. We'll begin with register mode. Register mode is used when the operand is located in one of the general registers. To indicate register mode, you use the notation RN in the operand specifier field of the instruction. N represents the number of the register whose contents are to be used as the operand. Here's a simple instruction that uses register mode. The instruction, increment long word, directs the CPU to increment the integer long word contained in register 1. When this instruction is executed, the ALU increments the operand contained in R1 and returns the incremented value to the same register. Register mode provides fast access to data referenced by instructions. Because the operand resides in a register within the CPU, memory does not have to be accessed. This addressing mode allows a general register to be used as a counter, an accumulator, or for temporary storage of data. Operands are more commonly accessed from memory. The register deferred mode can be used for this purpose. This mode is represented by the notation RN enclosed in parentheses. The parentheses indicate that the specified register contains the address of the operand. Because the operand resides outside the CPU, a memory access is required to obtain the operand. Here, we've used the register deferred mode with the increment long word instruction. The CPU uses the address contained in register 1 to retrieve the operand from memory. The operand is incremented by 1 and is then returned to its former memory location. Another commonly used addressing mode is auto-increment mode. When this mode is specified, the selected register contains an address which is updated automatically by the CPU each time the instruction is executed. Auto-increment mode is very useful for processing a series of items contained in a list or table. In this example, the starting address of the list is contained in register 1. When the increment long word instruction is executed, the CPU uses the address to access the first operand on the list. The operand is then incremented by 1 and is returned to its original location in memory. When this instruction executes, the address in R1 is automatically updated, so it's now pointing to the second operand on the list. Note that the address is incremented by 4 because the data type being accessed is a long word containing 4 bytes. Thus, each time this instruction executes, the address in register 1 is incremented automatically, so it's pointing to the next item on the list. A similar addressing mode, called auto-decrement mode, lets you step through the same list in the reverse direction. With the auto-decrement mode, however, the address is decremented before the operand is retrieved from memory. Notice that the minus sign appears in front of the register designation in the notation. We've seen how the auto-increment and auto-decrement modes can sequentially access items in a list or table, moving from top to bottom or from bottom to top. But suppose you want to process just one specific entry in a list or table. You can do that with displacement mode. Displacement mode defines the location of an operand with respect to the beginning of this list. The operand's address is calculated from two parts: a base address, Rn, and a displacement value, D. In this example, register 0 points to the beginning of the list, and D specifies how far from the beginning the operand is located. When this mode is specified, the CPU calculates the address of the operand by adding the base address from register 0 to the displacement value, D. In our sample instruction, the displacement 5 tells us to count 5 long words down from the base address to find the operand. By changing the value of the displacement, a programmer can access any item of data in this list. So far, we've looked at a number of addressing modes that use the general registers to find instruction operands. The next addressing mode we'll examine is relative mode. With relative mode, the programmer can use a label, such as tally, to reference an operand. The operand labeled tally is located by means of an offset value. This offset is calculated by the assembler and represents the distance, in bytes, between the next instruction and the location of the operand. Here, the operand follows the instruction that refers to it, so the offset is a positive value. When the CPU fetches this increment tally instruction, the address in the PC is updated, so it's pointing to the next instruction. The CPU then calculates the address of the operand tally by adding the offset value to the updated address contained in the PC. Because the contents of the PC are used in this address calculation, the address of the operand tally is not absolute. It's always expressed relative to the current value in the PC. The use of relative mode enables programmers to write position-independent code. That is, code which executes correctly no matter where it resides in memory. If the location of this increment instruction changes, the location of the operand tally moves along with it. Thus, the offset stays the same, regardless of where the instruction is stored in memory. We've described a number of addressing modes that use the general registers and program counter to locate instruction operands. There are also several variations of indexed modes. Indexing is typically used to access individual items in arrays. The base address of the array is summed with an index value to produce the address of the operand. During program execution, the index value can be modified, so it's possible to reference any item within the array. An index value of 0 selects the first item in this array. An index value of 7 selects the last item. Indexing requires two general registers, one for the base address and the other for the index. Here, register 1 contains a base address, which points to the beginning of the array, and register 3 contains the index value. This example shows indexing in its simplest form. Other variations, which will not be discussed, allow more complex ways of accessing data. One advantage of using an index mode is that the index is automatically adjusted for the size of the data type. Therefore, programmers need only concern themselves with the number of items in the array and not with a number of bytes in the operand. An example of a typical use of indexing follows. Our example uses several of the data types, instructions, and addressing modes introduced in this unit. Suppose we have a table of integer values that must be converted to floating point values. This table can be of any length. We'll use n to represent the number of entries in the table of integers. Our task, then, is to convert one data type to another, moving sequentially through both tables. How can we perform this conversion easily on a VAX computer? Let's examine the requirements of the task. First, we need to specify the base address of each table. We'll place these addresses in a pair of general registers. Register 7 points to the beginning of the existing integer table, and register 8 points to the starting location of the floating point table that we want to create. Next, we need to step through the tables, one item at a time, to convert each long word integer to a floating point value. We'll use R6 as an index register to access individual items in both tables. The index value in R6 is added to the base address to produce the effective address of one item. Then the index value is incremented by 1, so it's pointing to the next item in the tables. For simplicity, let's say that our data types are consistent in size. We'll convert integer long words into F floating data, both of which are 32 bits in length. Now we're ready to specify the instructions and addressing modes to be used for this task. First, we need to load R7 and R8 with the correct base address. Also, we must clear R6 so it contains an initial index value of 0. 3 instructions are used to initialize the general registers. The first instruction, move address, places the base address of the integer table in register 7. Another move address instruction loads register 8 with the base address of the floating point table. We'll assume that we've defined our table variable somewhere. The third instruction, clear long word, clears register 6 so it's pointing to the first value in the integer table. Notice the addressing modes we're using. I-table and F-table are labels, so the mode in use here is relative mode. The labels tell the assembler to calculate offset values for these operands. R7, R8, and R6 refer to the contents of those registers, so the addressing mode is register mode. Once the registers are initialized, the conversions can be performed. We'll access the first integer long word, convert it to F floating, and place it in the new table. This convert instruction performs the necessary conversion from integer long word to floating point notation. Note that we're using index mode for both operands. The source, or first operand, is accessed by adding the base address to the index value in R6. The base address is obtained from register 7. The destination operand is created when the conversion takes place. The address of this operand is formed by adding the base address in R8 to the same index value in R6. The remaining steps of our task are to add 1 to the index value in R6 so it's pointing to the next entry in the table. The updated index is then compared against n, or the number of entries in the source table, to determine if the end of the table has been reached. If not, we branch back and execute the convert instruction again. These 3 operations, add, compare, and branch, can be performed with just one instruction called add 1 and branch if less than. This instruction has 3 operand specifiers. Each operand is accessed using a different addressing mode. The first operand specifier is a label, n, which represents the number of entries in the source table. The addressing mode is relative mode, which allows us to use a label to refer to the operand. The second operand specifier refers to the contents of our index register, R6. Therefore, we're using register mode for this operand. The third operand specifier is another label, loop, which defines the destination of the branch operation. Notice that we've added the label to the instruction in the line above as well. This operand specifier uses an addressing mode we haven't covered, which simply refers to the branch destination in the instruction stream. When this instruction executes, the index value in R6 is incremented by 1, so it's pointing to the next entry in both tables. Then, the incremented index value is compared to n. You'll recall that n specifies the number of entries in the table of long word integers. If the index is less than n, the program branches back to the label loop, and the convert instruction is executed again. These lines of code demonstrate some of the richness of the VAX instruction set. 2 instructions can be combined with the right addressing modes to accomplish a considerable amount of work. This brings us to the end of the unit on the VAX hardware architecture. Your course reference guide contains additional information if you're interested in further study in this area.